Aircraft engines come in many different forms, but they all have one fundamental purpose: to convert energy into useful propulsion. From the piston engines used in light training aircraft, to turbofans powering modern airliners, and turboshaft engines driving helicopter rotors, each engine is designed around a specific mission. But how should we classify these engines? What makes an inline engine different from a radial engine? How does a turbojet differ from a turbofan? And where do turboprops, turboshafts, propfans, ramjets, and modern electric propulsion fit into the picture? In this video, we'll explore the major types of aircraft engines, how they work, when they were developed, and the aircraft that use them. There is more than one way to classify aircraft engines. We can classify them according to their mechanical design, their method of producing power, or the way that power is converted into aircraft propulsion. For this video, we'll use a practical classification based primarily on the engine's operating principle and its propulsive output. Let's begin with one of the oldest and most widely recognized forms of aircraft propulsion, the reciprocating or piston engine. A piston engine burns a mixture of fuel and air inside cylinders. The expanding gases push the pistons, and the piston's reciprocating motion is converted into rotary motion by the crankshaft. The crankshaft then drives a propeller, which produces the majority of the aircraft's thrust. In an inline engine, the cylinders are arranged in a single row. This arrangement can provide a relatively narrow engine profile, although it can result in a long engine depending on the number of cylinders. The horizontally opposed engine places cylinders on opposite sides of the crankshaft. This arrangement is particularly important in modern light aircraft because it provides a compact engine with good balance and a relatively low profile. In a V-type engine, the cylinders are arranged in two banks forming a V. V-type aircraft engines were widely used during the development of high-performance piston aircraft, particularly before turbine engines became dominant. A radial engine arranges its cylinders around a central crankshaft. Radial engines became especially important during the golden age of piston-powered aviation. Their air-cooled construction and robust design made them well-suited to many military and transport aircraft. Less common configurations include X-type and H-type engines. These designs were developed to achieve high power while maintaining a relatively compact arrangement. Although they are not common in modern general aviation, they are important from an aircraft engine development and engineering perspective. The next major family is the gas turbine engine. Unlike a piston engine, which produces power through reciprocating pistons, a gas turbine uses a continuous flow of air through the engine. Air is compressed, fuel is added and burned, and the resulting hot gases expand through the turbine and exhaust system. Depending on the engine design, that energy can be used to produce jet thrust, turn a propeller, or provide shaft power. The turbojet is one of the fundamental gas turbine engine designs. Air enters the compressor and is compressed to a higher pressure. Fuel is then injected into the combustor and burned. The hot gases expand through the turbine, which drives the compressor. The remaining gas accelerates through the exhaust nozzle, producing thrust. In a turbojet, a large proportion of the engine's useful propulsive effect comes directly from the high-speed exhaust. Turbojets played a major role in the transition from piston-powered aircraft to jet aviation. The turbofan is the dominant engine type for modern commercial jet aircraft. A turbofan adds a large fan to the front of the gas turbine engine. Some of the incoming air passes through the engine core, while another portion flows around the core through the bypass duct. The fan accelerates a large mass of air, producing a significant portion of the engine's thrust. This allows modern turbofans to achieve much better propulsive efficiency than early turbojets, particularly at the speeds used by commercial airliners. High-bypass turbofans are now the standard propulsion system for most large commercial jet aircraft. A turboprop engine uses a gas turbine to produce shaft power that drives a propeller through a reduction gearbox. In this case, the propeller produces most of the aircraft's useful thrust. Turboprops are particularly effective at moderate speeds and relatively short routes, where propeller efficiency provides an advantage over pure jet propulsion. A turboshaft engine is designed primarily to deliver mechanical shaft power rather than direct jet thrust. The engine drives a power shaft, which can then be connected to a transmission or gearbox. Turboshaft engines are particularly important in helicopters, where the engine's shaft power is transferred through the transmission to the main rotor. Turboshaft engines are also used in some other applications where compact, high-power shaft output is required. What happens when engineers try to combine some of the efficiency of a turboprop with the speed capability of a turbofan? One answer is the propfan, also known as an open rotor concept. Propfans use highly advanced propeller designs, often with multiple swept blades, and are driven by turbine machinery. They have been investigated as a way to achieve very high propulsive efficiency while maintaining relatively high aircraft cruise speeds. Not every jet engine needs a conventional compressor. A ramjet uses the forward motion of the aircraft to compress incoming air. Air enters the inlet, slows down, and its pressure increases. Fuel is then added and burned, and the hot gases expand through the nozzle to produce thrust. Because a ramjet does not have a conventional rotating compressor, it is most useful at high forward speeds. A scramjet takes the ramjet concept even further. In a scramjet, airflow through the combustor remains supersonic. This makes the engine extremely challenging to design and operate, but it offers potential for very high-speed atmospheric flight. Scramjets are primarily associated with experimental and advanced high-speed propulsion rather than conventional aircraft. Another interesting concept is the turboramjet. This combines features of a conventional gas turbine and a ramjet system. At lower speeds, the turbine-based portion can provide propulsion. At higher speeds, the ramjet portion can become increasingly important. This type of combined propulsion system has been investigated for high-speed aircraft and missile applications. Aircraft propulsion is also moving beyond conventional piston and gas turbine engines. Electric propulsion uses electric motors to drive propellers or fans. Hybrid electric systems combine electric propulsion with another energy source, such as a turbine or piston engine. These technologies are being investigated for applications ranging from small aircraft and advanced air mobility to larger future aircraft. So, how do these engine types compare? A piston engine provides propeller shaft power for training and light aircraft. Turbojets produce jet thrust for high-speed aircraft, while turbofans power most modern airliners and many fighters. Turboprops provide efficient propeller propulsion for regional aircraft, while turboshafts deliver shaft power for helicopters. Ramjets, scramjets, propfans, and electric propulsion serve more specialized or emerging applications. So, which engine is best? There is no single answer. The best engine is the one that matches the aircraft's mission. Understanding engine types helps us understand how aircraft are designed to fly. Thanks for watching.